Hello, this next video is going over transformations of your parent functions. There's essentially 5 things that you can do to transform a parent function. One is to vertically translate it, so move it up or down. One is horizontal translation, moving it left and right. So horizontal and vertical translations. You can also reflect your function over the x or y axis. You can stretch your function or compress your function. Those are the 5 things you can do. What we're going to look at is how to do each one of those. I'm going to go over to Desmos, and we're going to start out. Let's just work with the function f of x equals x squared. So I have the parent function of a quadratic, and we'll also look at the square root of x. So f of x equals square root of x. In order to get the square root symbol, you can click the calculator at the bottom or the keyboard at the bottom and click square root. Also, as a shortcut, you can just type SQRT on Desmos. So, again, I'll need you guys to go to desmos.com, pull up the graphing calculator, and it should bring you here. And then you'll just type in these 2 functions. This link at the bottom is a whole lot of chaos. We're going to get to this in just a second. But for now, you'll just open a blank Desmos tab. All right. Once you've got that open, square root x. Once you've got that open, type in these functions, then we'll hide this second one. So let's say we're looking at f of x equals x squared, and we want to do a vertical translation. Well, according to our set of rules right here, all we have to do is add or subtract some value. And they're calling this the value d, or the variable d. So let's say I add 2. Well, that just shifted everything up 2 units. What if I added 3? Everything shifted up 3 units from the parent function. 7, moves up 7. If I instead subtract 8, moves everything down 8. So if you add or subtract a function or a value to the entire function, it just moves it up or down. Same thing will happen with this square root function. If we add 8, it'll shift it up 8 units. We subtract 1, shifts it down 1 unit. That's all vertical translations are. Those are arguably the easiest to work with. Next up, we're going to talk about horizontal translations. These, again, if you'll notice, they have f of x plus c inside of the arguments or inside of the function. So what's happening here is everywhere you see an x, replace it with x plus c. And that's going to give you your horizontal or vertical translation. Let's just look at a translation 2 units to the left. So we'll say x plus 2. Everywhere I see an x, I've got to replace it with x plus c. In Desmos, I have to be careful about this. So what I'm going to do is add a parenthesis to the left and right of x, add a c in that set of parentheses. In this case, I think we said a translation of 2, so yeah, we'll do 2. All right, so this is a horizontal translation. So everywhere I saw an x, I replaced it with x plus c, or in this case, x plus 2. What this does is it shifts everything 2 units to the left, or the opposite of what you would think it does. If we're adding 2, well, we're going 2 to the left. The reason for that being is, well, originally in the function, f of x equals x squared, when we plugged 0 into the equation, we got 0 out of the equation. Now, in order to get 0, or the output of 0, what we need to do is we need to have a 0 right here being squared. Well, in order to turn this into 0, we need a -2. So you've kind of got to cancel out whatever is in here in order to get back to the original function. And so this does the opposite of what you would think it does. If you add 2, you go 2 to the left. If I subtract 7, move 7 to the right. All right. It'll work the same way with the square root. So again, it has to be inside the argument. So in this set of parentheses, we're going to do plus 2 to the left 2, plus 4 to the left 4, so on and so forth. All right. So let's go back to our parent functions. All right, so that's vertical and horizontal translation. So that's just shifting your units or your function to the left or to the right or up and down. Next up are reflections, stretches, and compressions, and these are all sort of linked to each other. If we look at a reflection over the x-axis, you just take your function and multiply by -1. That's what that negative sign is. If I just take this and multiply by -1, ignore this one for now, flips it across the x-axis. All this does is it takes all the positive values and turns them negative. So if I look at 2 as an input, 4 as an output, well, if I were to multiply by -1, when I do 2 squared, that's 4, times -1, that's -4. Same thing with every other point on this graph. Same thing happens with this right here. Multiply by -1, and we flip the graph. And again, this doesn't just work for these two parent functions. These are just the nicest functions I could show you. And I could show you them all at the same time, but it would look like this. We're just going to look at these two for now. All right, next up is a reflection over the y-axis. So everywhere you see an x, replace it with x minus 1, similar to this horizontal translation. So instead of an x, I do -x, which doesn't change anything for a quadratic. So let's look at the square root function. -x. What this does is it pretty much flips everything across the y-axis, or exactly as that chart said. And what we've got going on here is previously, if I tried to plug in 9, well, I could plug that in. The square root of 9 is 3, and I get this output. Now that we have a negative value in here, if I try to plug in 9, I'll end up looking at what is the square root of -9, which is imaginary. It wouldn't show up on a regular chart. So this is not part of our domain. It's not even part of the function. Actually changes our entire domain. What I could do is I could look over here. If I plug in -9, when -9 times -1 is 9, square root of 9 is 3. Plug in -9, get out 3 now. So it just takes all the values and flips them. Let's cancel that. Right, those are your reflections. Next up is a vertical stretch or vertical compression. And that's if you take your entire function and multiply by some value a. So let's say I multiplied this entire thing by 2. Oh, that doesn't look like it changed much, but it did. So we're slightly steeper whenever we do 2. If we plug it in 5, we're a lot steeper, actually. If we plugged in 10, we get really, really, really steep. What this is doing is essentially whenever I plug in, let's say the number 10. Originally in my function, when I plugged in 1, I did 1 squared and I got out 1. Well, now what's happening is when I plug in 1 and I do 1 squared, I end up with 1 squared or 1 times 10, or an output of 10. If I do 2, I plug in 2, 2 squared is 4, 4 times 10 is 40. Well, my output is now way up here at 40 instead of 4. And so it makes our function increase a whole lot faster than it did before. If we look at square root function, I plug in 10 here, the same thing happens. And when I plugged in, let's look at 1. When I plugged in 1 before, the square root of 1 was just 1. I got this point right here. But now when I plug in 1, I end up with 1 times 10. The square root of 10 is 3 point something, or 3.14, 3.16. Right. So all of my outputs will grow much, 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 much faster. And it almost looks like it's sort of pushing or pulling this function. And all of these will end up looking like they're doing that. What you're going to end up with is we were just looking at a vertical stretch. So it sort of stretched our function vertically, almost pulled it upwards. If we were to look at the same thing, but instead of having our value be greater than 1, we had a value of less than 1, we would have what's called we would end up with what's called a vertical compression. So let's say instead of 10, we did 1 divided by 10. I'll just do 1 and hit the slash on my keyboard, type in 10. That makes it wider, or it almost compresses it. It looks like it's pushing the graph down towards the x-axis. And this will look a whole lot more, or will be a whole lot more visible once we look at all of this chaos. But for now, it's just a vertical compression. So we're pushing it sort of closer towards the x-axis. Or if it's larger than 1, sort of pushing it away from the x-axis. Same thing here. I do 0.1 or 1/10, pushing it towards the x-axis. 10, pushing it away from the x-axis. All right, final type of transformation is horizontal compressions. That's if I, again, replace all my x's with b times x. We're just going to look with a shrink or a stretch or compression. We'll do 4. So this will end up giving us a compression. Sort of works the opposite of the vertical stretches and compressions. The larger the number, the more it compresses. So if I put a 4 here, and I guess square, it's not really the best function to use for this. It would probably be better to see it on a exponential function. But we are also sort of compressing this or pushing it towards the y-axis as we get larger and larger and larger with our value in front of x, or our b value. Same thing will happen here. If I do 10, again, we are pushing it closer towards the y-axis and away from the x-axis. If I do a value of, let's say 1/10, or something less than 1 but greater than 0, what I'm going to end up with is a horizontal stretch. Again, this one will be much, much nicer to see on this graph. So it looks like it's pulling my graph out horizontally. So my graph is shifting to the right and to the left, or getting much wider. And if I do a value greater than 1, same thing happens, or opposite thing happens. We push horizontally, or try to squish that function together. All right, so these last two transformations are a bit more confusing, but we're going to tie all of these sort of together using this right here. So what I'm going to show y'all real quick is if I have a function, so f of x, let's say equals x squared. All of your transformations can sort of be modeled by this equation right here. A times f of bx plus c plus d. Oh, and we don't need that for a set of parentheses. What this a value is going to do is it's going to do the same thing as over here, going to give you a vertical stretch. It's a times the function. B value, what it's going to do is going to give you a horizontal compression or stretch. And it's b times x, that's inside the argument of the function. This plus or minus c is also inside the argument of the function, so both of these are here. Plus d is outside of the function, just added at the end. All right, so in this example, a is our vertical stretch, b is our horizontal stretch, c will give us a horizontal shift, so just moving it to the left or right. D will give us a vertical shift, moving our function up and down. All right. So looking at this function right here, what we're going to do is model it to be very similar to this, and I'm going to add what are called sliders for a, b, c, and d. We'll do a times bx plus c, all plus d. So I'm making my function look like this form right here. If I were to do the same thing, and again, I'll add a slider for all of these. All right, so what Desmos does with the sliders, ignore this. Essentially, it just sets it to a value. So let's say a was 1, b was 1. Let's just have everything be 1. What this is doing right here is it's taking this equation and it's giving me this. I'm going to say 1 times 1x plus 1 plus 1. this actually gives me a shift 1 unit up and 1 unit to the left. And we don't technically need to write these if they're 1. It just gives us this equation or this function. If I were to replace a with, say 5, and b with 3, and c and d with 6 and 8. Right. Now what this is doing is it's giving us this function. Again, I'm going to copy paste this. It's saying a is 8, b is 6. Oh, sorry about that. I have them backwards. Let's rewrite that. All right, so a is 5, b is 3, c is 6, d is 8. All right, so if we look at our transformations over here, again, a is our vertical stretch, b horizontal stretch, c will give us a horizontal shift, d will give us a vertical shift. All right, so this 5 corresponds to a, or our vertical stretch or compression. 3 corresponds to b, or our horizontal stretch or compression. 6 corresponds to c, horizontal shift. 8 responds to d, vertical shift. And so this is actually what's happening when I set these values here to this function. So this function being graphed right here is this. So if we actually look, our function is shifted 1, 2, 3, 4, 5, 6 units to the left, 8 units up. So that's really nice. We can look at our horizontal and vertical shifts easily. We do have a vertical stretch. So it's almost pulling the function up. And again, with a quadratic by itself, it's really hard to see because it's symmetric about the x-axis. And we also have a horizontal compression, so it's pushed in. What I've done is, if you copy paste the link from the Blackboard session, I've taken every single parent function and I've plotted them all in this form right here. So if I change the a value on the slider in this, it changes every single one of these parent functions. What I'm going to do, we're not too worried about arctangent, arcsine, arccosine, etc. We're going to close all of these out. All right. Oh, we don't need these right here. All right, so these are our basic functions. Typically, a and b are being multiplied by variables or by the values. So if we set those to 1, it should give us the parent function. C and d are being added if we set those to 0. These are all the parent functions, how they originally look. So we have the linear function, just a line, a quadratic function, we have an absolute value function, our square root function, cubic function, exponential, and a logarithmic. These are all sort of overlapped on top of each other. I just want to show you guys what happens to every single parent function when you change the a, b, c, or d value. So if you don't pay attention to anything else, this is probably the most useful piece of information to know. So all of these parent functions are graphed here. Let's say I change the d value. Every single function just shifts straight up. So if I change it to 1, every function is shifted up 1 unit. If I change d, I think by default, your sliders may actually be set between -10 and 10, but that's fine. It won't change anything. So again, I can go all the way up to 20, shift these up 20 units. They're at 20 units. Go to -20, shift it down 20 units. I'm going to set that back to 0. I'm just going to type 0 instead of fighting it. Okay. All right, now let's look at my C values. Let's say I change the C value. Well, as I change C, again, I get that horizontal shift. Just like this image is telling me. If I change the C value, I shift left or right. So if I make it a positive 10, everything shifted to the right 10 units. Make it, oh, that's the D value. Make it negative 5, everything shifted to the right 5 units. So it doesn't matter what kind of parent function you have. If you change a C or D value, it'll translate it to the right or to the left or up and down. Now we're going to do the same thing with B. So B is this value inside the parentheses. If I change the B value, or actually, let's just make it positive for now. We'll stay positive. So if I increase B, what's happening to all these functions is a horizontal compression, or they're getting pushed. It's almost like someone's taking invisible hands and smushing all of these functions from the left and right towards the y-axis. If we look at what happens when B is less than 1, but greater than 0, oops, sorry, right here, what we're going to end up with is a horizontal stretch, almost like those hands are now pulling the functions away from the y-axis. And whenever this B value turns negative, what we end up with is the same exact thing, just flipped. So as B becomes more and more negative, we still end up with vertical compressions. It's just everything shifted. As B decreases, everything expands. So as B gets larger, either in the positive or negative direction, you squish things horizontally. All right, so let's set that back to 1. And now we're going to look at A, or the vertical stretches and compressions. So as A gets larger, what we end up with is something really similar, but not quite the same. So if we look at A, and again, it was set originally to 1. If we increase A, again, same thing's happening, but we're not being pushed horizontally from side to side. It's more so these functions are all being dragged up and down. So this is really shown very well with a logarithmic function right here. So if we look at what happens when we change B, and this function is pushed towards the x-axis, or towards the y-axis. But as we change A, it's more like it's dragged away from the x-axis, or it's being pulled up. All right. And again, as these go negative in the A value, they all flip among or across the x-axis, and same thing happens with a vertical stretch or compression. All right, and you can play around with these and just see what happens. If you want, let's say, just to look at linear functions, we'll keep the linear function up right here. We just want to look at the line. If I want to shift this up 5 units, I would change the D value to 5. You can also do multiple transformations at once. So I also wanted to shift it to the left. Let's go, I guess a line is a terrible equation to use for this. Let's use the exponential. I'll kind of label these all off for you. This is a linear equation. This is a quadratic. Sine and cosecant, don't worry about. Absolute value, square root, cubic, exponential, logarithmic. All right, so let's look at the exponential function. Let's say we want to shift it 5 units to the left, and then 3 units down. Well, we can do that. Say we wanted to horizontally compress it. We can set that up to 20 and it would horizontally compress our function by a lot. We also wanted to vertically stretch it. We can set that to maybe 15. It would stretch our function by a lot. And you don't have to set the exact same values as I do. This is really just a tool to show you what happens as you change all of your numbers. All right, that's it for this video. So if you want to turn these back on again, this could be helpful in your homework or determining what's going on with each of the transformations. All right. So again, if you have any questions, let me know. And that's the end of the video.